On October 24, 2025, something appeared on the data screens at the Meerkat Radio Telescope facility in South Africa that made astronomers question everything they thought they understood about interstellar visitors. A signal, not just any signal, a radio spectrum from 3I Atlas, the interstellar comet that had been traveling through our solar system for months, silent and unremarkable to radio astronomers who never expected to hear anything from it. And here's what makes this moment historic. This is the first time in human history that any radio telescope has ever captured a radio spectrum from an interstellar object, not from 1I Oumuamua, not from 2I Borisov. Those visitors passed through our cosmic neighborhood completely silent at these frequencies. But 3I Atlas spoke, and according to every model, every textbook, every precedent we had about how interstellar comets behave, it shouldn't have. Comets from beyond our solar system aren't supposed to emit detectable radio frequencies in the way Meerkat observed. They're radio quiet, invisible to instruments designed to listen for electromagnetic whispers from the cosmos. Yet, there it was, unmistakable, natural, and completely unprecedented. If you're as curious as the scientist who just saw this data, hit that like button and drop a comment telling me what you think we're about to discover, because what comes next changes everything we thought we knew about objects from beyond our solar system. Before we understand why October 24th matters, we need to understand what silence sounds like when you're listening to the universe. Radio astronomy isn't like pointing a camera at the sky and snapping a picture. It's more like pressing your ear against the cold metal door of an empty warehouse, straining to hear anything beyond the hum of cosmic background noise. And when it comes to comets, especially interstellar comets, that silence has been absolute, predictable and scientifically sound until now. Here's what every astronomer expected when they pointed instruments at 3I Atlas. Nothing. Not because they weren't curious, but because precedent had trained them not to hope. When 1I Oumuamua tumbled through our solar system in 2017, radio telescopes tracked it obsessively, searching for any hint of electromagnetic activity. They found silence. When 2I Borisov arrived in 2019, scientists repeated the process, this time with more advanced instruments and longer observation windows. Again, silence. These weren't failures of technology. They were confirmations of what we already understood about comets. They're chunks of ice, rock, and frozen gases held together by gravity and time. When they approach a star, solar radiation heats their surfaces, causing volatile materials to sublimate and create the spectacular tails we associate with comets. But this process, as visually dramatic as it appears through optical telescopes, doesn't produce radio emissions in the frequencies we typically monitor. It's a light show without a soundtrack. 3I Atlas was supposed to follow this script exactly. Discovered through optical observations months earlier, it had been classified as an interstellar comet based on its hyperbolic trajectory. A path that proved it originated from beyond our solar system, gravitationally unbound to the sun. It was approaching perihelion, the closest point in its journey to our star, which occurred on October 29, 2025, at a distance of approximately 203 million kilometers, 1.36 astronomical units. This was the phase when comets become most active, when solar heat penetrates deep enough to vaporize subsurface ices and trigger outgassing events. Optical telescopes were watching. Infrared instruments were collecting data. Ultraviolet spectrographs were analyzing its chemical composition. But radio astronomers, they were treating 3I Atlas like background work, routine monitoring that nobody expected to yield results. After all, 2 previous interstellar visitors had taught us that radio silence was the norm. But something about 3I Atlas was already disturbing astronomers long before Meerkat's detection. Images captured in the weeks leading up to perihelion showed anomalies that didn't fit standard cometary behavior. There was no visible tail, not a faint tail, not a diffuse tail, no tail at all. What should have been a glowing arc of dust and gas streaming millions of kilometers behind the comet was instead just a concentrated blob of light, compact and structurally ambiguous. Observers noted color changes, with 3I Atlas appearing bluer than the sun and a typical spectral signature for objects of its presumed composition. Then there was the non-gravitational acceleration, subtle trajectory deviations that couldn't be explained by the sun's gravity alone. These deviations suggested outgassing jets of vapor escaping asymmetrically and producing tiny thrust effects that nudged the comet off its predicted path. Every one of these clues pointed toward an active degassing object. Yet optically, it remained stubbornly enigmatic. It was this collection of visual oddities that prompted a few research teams to do something unconventional. They decided to point radio telescopes at 3I Atlas anyway, not because they expected to find anything, but because the comet was behaving strangely enough to justify looking. The observation window was narrow. On October 24th, 3I Atlas was just 3.76 degrees from the sun as viewed from Earth, so close that solar radio interference would make observations extraordinarily difficult. Most astronomers avoid this proximity entirely. The sun is a roaring bonfire of electromagnetic noise that drowns out faint signals from distant objects. But the Meerkat team knew that after October 30th, 3I Atlas would disappear behind the sun from Earth's perspective, hidden in solar conjunction for weeks if they wanted to capture radio data during peak outgassing. October 24th was one of their last chances, so they aimed the array. 64 radio dishes, each 13.5 meters in diameter, synchronized to function as a single massive ear pressed against the cosmos. The observation began like any other data streaming in engineers monitoring signal-to-noise ratios. Astronomers mentally prepared for the usual result: nothing. Radio telescopes don't deliver instant gratification. The data requires processing, calibration, filtering out terrestrial interference and solar contamination. Hours passed between observation and analysis, and in those hours, nobody at Meerkat suspected they had just witnessed history. It wasn't until the processed spectrum appeared on their screens that the realization hit. They were looking at a signal, a natural radio emission at 1,600 megahertz with distinct features that told a story nobody expected to read. To understand what Meerkat accomplished on October 24th, you need to understand what Meerkat is, not just a telescope, but a technological symphony designed to hear whispers from the edge of the observable universe. Located in the Karoo Desert of South Africa, one of the most radio-quiet regions on Earth, Meerkat consists of 64 offset Gregorian dishes arranged in a formation that maximizes both sensitivity and resolution. Each dish is a precisely engineered listener capable of detecting electromagnetic radiation at frequencies ranging from 580 MHz to 14.5 GHz. But it's in the L-band truly excels. This is the frequency where hydroxyl radicals, the byproducts of water molecules being torn apart by solar ultraviolet radiation, leave their fingerprints in the cosmic radio spectrum. Radio astronomy is an exercise in patience and precision. Unlike optical telescopes that capture photons almost instantaneously, radio telescopes collect electromagnetic waves over extended periods, integrating signal over time to distinguish genuine celestial sources from noise. The longer you observe, the clearer the signal becomes, assuming there's a signal to find at all. Meerkat's design philosophy embraces this reality. Its dishes operate in unison. Their data combined through a process called interferometry, which effectively creates a single telescope with a collecting area equivalent to all 64 dishes combined. This makes Meerkat one of the most sensitive radio instruments in the southern hemisphere, capable of detecting sources billions of light years away, or in the case of 3I Atlas objects much closer but far fainter than anyone anticipated. The observation session on October 24th was meticulously planned but cautiously optimistic. The team knew they were working under challenging conditions. At 3.106 degrees from the Sun, 3I Atlas was bathed in solar radio emissions, a cacophony of electromagnetic noise generated by solar flares, coronal activity, and the Sun's general plasma turbulence. Filtering this interference would require sophisticated calibration techniques and post-processing algorithms designed to isolate signals originating specifically from the comet's coordinates. The observation window was narrow, a few hours at most, before the comet's position relative to the Sun made further observations impractical. Engineers monitored the array's performance in real time, ensuring that all 64 dishes remained locked onto the target coordinates, tracking 3I Atlas as it moved against the background sky. When the raw data began streaming into Meerkat's processing servers, nobody was watching with bated breath. This was routine work, the kind of observation that fills research logs more often than it fills press releases. The data would be archived, processed during routine analysis cycles, and likely reviewed weeks later, when teams had time to sift through the accumulated observations. But radio astronomy has a way of surprising even the most skeptical researchers. As the data passed through calibration pipelines, correcting for atmospheric distortion, subtracting terrestrial interference, isolating the frequency channels relevant to cometary emissions, a pattern began to emerge, not noise solar contamination. A signal at first, it appeared as a subtle enhancement in the 1600 megahertz range, a region of the spectrum where hydroxyl radicals emit and absorb radiation. But what made astronomers pause wasn't just the presence of emission, it was the structure of that emission. Embedded within the signal were absorption notches, narrow dips in intensity at precisely 1665 millihertz and 1667 millihertz. These weren't random fluctuations. They were the unmistakable signatures of hydroxyl molecular transitions, the quantum mechanical fingerprints left when OH radicals interact with radio waves at specific frequencies. Every radio astronomer recognizes these lines. They appear in star-forming regions in the envelopes of dying stars in the molecular clouds where planets are born. But they had never appeared in the spectrum of an interstellar comet, not until October 24th, 2025. The realization didn't arrive all at once. It unfolded in stages as different team members reviewed the processed data and cross-referenced it with theoretical models. Someone flagged the absorption features. Someone else confirmed the frequency precision. A third researcher pulled up archival observations of solar system comets for comparison. The pattern matched. The physics made sense, and the implications were staggering. 3I Atlas, an object from beyond our solar system, was not only detectable at radio wavelengths, but was actively producing a hydroxyl envelope dense enough to leave spectroscopic signatures. This wasn't a faint marginal detection requiring statistical arguments to validate. It was clear, quantifiable, and scientifically robust. Meerkat had not only heard 3I Atlas, it had decoded its chemical voice. What made this moment even more profound was the historical context. Attempts to detect radio emissions from 2I Borisov, the previous interstellar comet, had yielded nothing, despite extensive observations with multiple facilities. The assumption had been that interstellar comets, whatever their composition, simply didn't produce radio-detectable outgassing at levels measurable from Earth. Perhaps they were too small, too distant, or composed of materials that sublimated without generating significant OH densities. But 3I Atlas shattered that assumption. It proved that interstellar visitors could speak in radio frequencies. that their chemistry could be interrogated through electromagnetic channels previously thought irrelevant. And it raised an immediate, urgent question. If Meerkat detected this signal on October 24th, what else were we missing? Let's talk about what it means to see something in a spectrum. When astronomers analyze light, whether visible, infrared, ultraviolet or radio, they're not just measuring brightness. They're reading a chemical story written in wavelengths and frequencies, a narrative encoded by the atoms and molecules that emitted or absorbed that light. Every element, every compound, every molecular bond has a unique spectroscopic signature, a set of wavelengths where it interacts with electromagnetic radiation in characteristic ways. Hydrogen emits at 1420 MHz. Carbon monoxide absorbs at specific infrared bands, and hydroxyl radicals, OH molecules composed of one oxygen atom bonded to one hydrogen atom, leave their mark at 1665 MHz and 1667 MHz in the radio spectrum. The Meerkat detection of 3I Atlas revealed both of these hydroxyl lines, clear and unambiguous, superimposed on a broader emission continuum at 1600 milliyears. This is the first radio spectrum ever obtained from an interstellar object. Not a tentative hint requiring pages of statistical analysis to defend, not a marginal signal buried in noise that might or might not be real. A spectrum, quantitative, reproducible, scientifically definitive. The presence of those absorption notches at 1665 and 1667 MHz is diagnostic. It tells us that 3I Atlas is surrounded by a cloud of hydroxyl radicals, molecules created when solar ultraviolet radiation strikes water ice on the comet's surface and tears H2O molecules apart. One water molecule breaks into one hydroxyl radical and one hydrogen atom. The hydroxyl radicals then populate a region around the comet called the coma, a diffuse envelope that can extend hundreds of thousands of kilometers into space. This is standard cometary physics when applied to solar system comets. We've studied hydroxyl emissions from periodic comets like Hale-Bopp, from long-period visitors like Hale-Bopp, from dozens of smaller objects that pass through the inner solar system every year. But we had never confirmed this process occurring in an interstellar comet using radio observations. When 2I Borisov was studied in 2019, radio telescopes searched for hydroxyl signatures and found nothing. The assumption was that either the comet wasn't outgassing enough water to produce detectable OH densities, or that observational conditions, distant solar angle sensitivity limitations, prevented detection. But 3I Atlas changed the equation. It proved that interstellar comets carry water ice volatile enough to sublimate when heated, that this sublimation produces hydroxyl envelopes comparable to solar system comets, and that with the right instruments and timing, we can measure these envelopes from Earth. Now, before we go further, we need to address something that's been circulating on social media and conspiracy forums. The so-called Fibonacci signal supposedly detected from 3I Atlas at 1420 MHz. Let's be absolutely clear, this never happened. The viral claims about mysterious pulses at 1420 MHz, often called the waterhole frequency in SETI research, were completely fabricated. No credible astronomical institution, no peer-reviewed publication, no verified source has ever confirmed such a detection. The Meerkat observation at 1600 MHz is the real scientifically validated discovery, and it has nothing to do with alien communication or mathematical sequences. It's astrophysics, not science fiction. The hydroxyl absorption lines at 1665 and 1667 MHz are natural consequences of photodissociation chemistry predicted by decades of laboratory research and cometry models. There's no mystery here requiring exotic explanations, just extraordinary science applied to an unprecedented object. What makes the Meerkat spectrum scientifically valuable isn't just that it confirms water outgassing, it quantifies it. The depth and width of those absorption lines at 1665 and 1667 megahertz encode information about the density of hydroxyl radicals in the coma, the temperature of the gas, and the rate at which water is being converted into OH and H. By modeling these spectral features, astronomers can estimate that 3I Atlas was producing water vapor at a rate of hundreds of kilograms S during the October 24th observation. That's a significant outgassing rate, comparable to moderately active solar system comets at similar distances from the Sun. It means that despite 3I Atlas being 203 million kilometers from the Sun at the time, roughly 1.4 astronomical units farther than Earth's orbit, it was hot enough and volatile-rich enough to sustain vigorous sublimation. This is where the story starts to fracture into competing threads. Because while the radio data unequivocally confirms outgassing, the optical data tells a contradictory story. Images of 3I Atlas taken around the same time show a compact, concentrated light source with no visible tail, no diffuse coma structure, no obvious evidence of the massive gas production that Meerkat detected. And this isn't a case of observers looking in the wrong place or using insufficient instruments. Hubble Space Telescope observations in September 2025 detected water vapor spectroscopically, confirming that H2O was present. JWST observations in August identified carbon dioxide and hydrogen cyanide in the comet's outgassing products. These are volatile molecules that sublimate aggressively when exposed to solar heat. Yet optically, 3I Atlas remained enigmatic, a bright blob devoid of the structural features we associate with active comets. So we're left with a paradox. Radio astronomy says 3I Atlas is outgassing water and producing a hydroxyl envelope. Infrared spectroscopy confirms carbon dioxide and other volatiles. Ultraviolet observations detect water vapor. Every measurement across the electromagnetic spectrum screams active comet. But point an optical telescope at it and you see something that looks nothing like the textbook definition of an active comet. No tail, no visible coma, just light. And that contradiction, that tension between what different instruments tell us, is where the real investigation begins. Because if Meerkat heard a radio signal that shouldn't exist according to our expectations, then maybe our expectations about how interstellar comets behave were never correct to begin with. Imagine you're a detective arriving at a crime scene where all the evidence points to an event that clearly happened, except there's no visible trace of it anywhere. The forensic data says someone broke through a window, shattered glass particles in the carpet, chemical residue consistent with forced entry, fingerprints on the frame, but when you look at the window, it's perfectly intact. No cracks, no missing panes, no sign of damage. That's the situation astronomers face with 3I Atlas. Every measurement says it's outgassing, shedding mass, actively sublimating water, ice, and volatile compounds. But when you look at it through optical telescopes, it appears as a featureless point of light with no cometary tail. Comets are defined by their tails. Not scientifically, you don't need a tail to be classified as a comet, but culturally, visually, historically, tails are what make comets iconic. There are two types, dust tails and ion tails. Dust tails form when solar radiation pressure pushes small particles away from the comet's nucleus, creating a curved yellowish arc that can stretch millions of kilometers. Ion tails are straighter, blue-tinted, and formed when solar wind streams of charged particles from the Sun interacts with ionized gas molecules in the coma, dragging them into long, glowing structures. Both tails are evidence of outgassing of material leaving the nucleus and spreading into space, and both should be visible when a comet approaches perihelion, the period of peak activity when solar heat penetrates deep into the icy nucleus. 3I Atlas passed perihelion on October 30th, 2025, at a distance of 203 million kilometers from the Sun. That's roughly 1.36 astronomical units. a proximity where solar flux is strong enough to trigger aggressive sublimation in most comet materials. Water ice, carbon dioxide ice, methane, ammonia. These are the compounds that vaporize first, creating the pressure that fractures surface layers and releases dust particles. By all accounts, 3I Atlas should have been visually spectacular at perihelion, sporting a tail that rivaled or exceeded those of typical solar system comets at similar distances. Instead, observers reported what can only be described as underwhelming: a bright, compact light source with no discernible tail structure. Some images suggested faint, diffuse extensions, but nothing remotely resembling the classical cometary appearance. This is where Dr. Loeb's observations become critical. Loeb, chair of Harvard's astronomy department and a researcher known for pushing the boundaries of conventional interpretation, has been tracking 3I Atlas since its arrival trajectory became clear. His team noted non-gravitational acceleration, deviations from the path predicted by gravitational forces alone. These deviations are telltale signs of outgassing. When jets of vapor escape asymmetrically from a rotating nucleus, they produce tiny rocket effects that nudge the comet slightly off course. The magnitude of acceleration observed in 3I Atlas suggests outgassing rates significant enough to alter its trajectory measurably over weeks. And here's the kicker. Non-gravitational acceleration of this strength should correlate with visible outgassing with plumes, jets, or tails that optical instruments can photograph. Loeb also documented color changes in 3I Atlas. Spectroscopic measurements showed it reflecting sunlight with a blue-shifted spectrum, meaning it appeared bluer than the sun's natural color. This is atypical. Most comets reflect sunlight with colors that match or trend slightly redder than the solar spectrum, consistent with surfaces covered in organic compounds and silicate dust. A blue coloration suggests either unusual surface composition or scattering effects caused by very small particles, nanometer scale grains that preferentially scatter shorter wavelengths of light. Either way, it's another anomaly layered onto an already perplexing object. Then there's the mass loss estimate. Preliminary models based on trajectory analysis and brightness variations suggest 3I Atlas may have lost approximately 13% of its total mass between initial detection and perihelion. 13%. That's not a minor shedding of surface layers, that's catastrophic mass loss. The kind of disintegration event that produces spectacular displays in solar system comets. Objects that lose that much mass typically fragment, creating multiple nuclei and extensive debris fields that stretch across enormous distances. 3I Atlas showed no such fragmentation in optical images. It remained coherent, structurally intact, stubbornly tailless, despite hemorrhaging mass. So what's happening? How does an object lose 13% of its mass through outgassing vigorous enough to produce detectable hydroxyl clouds at radio wavelengths and non-gravitational acceleration measurable across millions of kilometers, yet leave no visible tail in optical observations? Let's walk through the hypotheses, starting with the most scientifically conservative hypothesis 1. The tail exists, but we can't see it because dust production is extremely low. Radio telescopes detect gas, specifically hydroxyl radicals and water vapor. Optical telescopes primarily see dust because dust particles scatter sunlight efficiently and create the visible structures we call tails. If 3I Atlas is outgassing almost pure gas with minimal dust entrainment, then Meerkat and Hubble would detect activity while optical telescopes see nothing. This scenario requires that the comet's composition is gas-rich and dust-poor, a profile that differs from typical solar system comets but isn't physically impossible. Perhaps interstellar comets form under conditions that favor volatile ices over silicate grains, leading to gas-dominated outgassing. Hypothesis 2. The outgassing is highly directional, with jets pointing away from Earth's line of sight. Comets don't outgas uniformly. Their surfaces are heterogeneous, with active regions where sunlight directly illuminates volatile rich patches and inactive regions covered by dust mantles that insulate subsurface ice. If 3I Atlas has active jets on its far side, the hemisphere facing away from Earth during our observation windows, then the material ejected would stream into space in directions we can't optically observe. Radio emissions from the hydroxyl coma would still reach us because the coma expands spherically over time, eventually enveloping the nucleus. But the initial concentrated jets responsible for tail formation would be invisible from our vantage point. Hypothesis 3. Composition differences between interstellar and solar system comets lead to different outgassing dynamics. 3I Atlas formed around another star in a protoplanetary disk with different elemental abundances, different temperature gradients, different radiation environments. Maybe interstellar comets are enriched in supervolatiles, substances like carbon monoxide or nitrogen that sublimate at much greater distances from the sun than water ice. These supervolatiles could drive early outgassing that depletes the nucleus of its most volatile components before it even reaches the inner solar system, leaving behind a depleted, less active object by the time it passes perihelion. The hydroxyl emissions Meerkat detected might represent residual water outgassing from a nucleus that's already lost most of its volatile inventory. Hypothesis 4. Observational bias. 3I Atlas was observed at 3.76 degrees from the Sun on October 24th. That proximity means observing through immense scattered sunlight, both from Earth's atmosphere and from interplanetary dust. Faint tail structures could be completely washed out by this background glare. Invisible not because they don't exist, but because they're drowned in light pollution. Similarly, if the tail is composed of extremely fine particles or diffuse gas, it might fall below the detection threshold of the instruments used, requiring longer exposures or different filters to reveal. Each hypothesis has merit. Each explains some aspects of the observations while leaving others unresolved. And that's the hallmark of genuine scientific mystery. Not a question with a single obvious answer, but a problem that resists easy resolution, forcing researchers to collect more data, refine models, and challenge assumptions. What we know for certain is this. Meerkat detected hydroxyl absorption lines, confirming water outgassing. Hubble detected water vapor spectroscopically. JWST detected carbon dioxide and hydrogen cyanide. Non-gravitational acceleration confirms asymmetric outgassing sufficient to alter the comet's trajectory. And yet, optically, 3I Atlas defies categorization. It's a comet that behaves like a comet in every measurable way, except the one that matters most to human eyes. Appearance. Chemistry is a language older than words, written in the quantum interactions between atoms and energy. When Meerkat detected absorption lines at 1665 and 1667 memoirs, it wasn't just seeing hydroxyl radicals, it was reading a chemical biography of 3I Atlas. A history written in molecular bonds that formed light years away around a star we'll likely never identify. To understand what those absorption lines mean, we need to zoom down to the molecular scale, to the moment when water transforms under the sun as relentless radiation. Water molecules H2O, two hydrogen atoms covalently bonded to one oxygen atom, are extraordinarily stable. They can survive for billions of years locked in ice, preserved in the frozen hearts of comets, drifting through the void of interstellar space. But stability ends when sunlight arrives. Ultraviolet photons carry enough energy to break chemical bonds, splitting H2O molecules into fragments. One hydroxyl radical OH and one hydrogen atom H. This process, called photodissociation, happens continuously on the sunlit side of any comet approaching a star. It's not explosive. It's gentle, statistical, inevitable. Every second, billions of water molecules sublimate from the comet's surface, drift into the surrounding coma, and are torn apart by UV radiation. The hydrogen atoms, being lightweight and fast-moving, escape into space. The hydroxyl radicals, heavier and slower, linger, accumulating into a diffuse cloud that can extend hundreds of thousands of kilometers around the nucleus. These OH radicals aren't just chemical debris. They're quantum systems with discrete energy states, and they interact with electromagnetic radiation at specific frequencies determined by their rotational and vibrational modes. In the radio spectrum, hydroxyl radicals absorb photons at 1665 MHz and 1667 MHz, corresponding to transitions between different rotational energy levels. When radio waves pass through a cloud of OH radicals, photons at these exact frequencies get absorbed, creating dark lines in the spectrum, absorption features that act like fingerprints, unmistakable and diagnostic. The depth of these lines tells us how many hydroxyl radicals are present. The width tells us about temperature and velocity dispersion. The ratio between the two lines reveals the physical conditions within the coma. For 3I Atlas, the presence of both lines at expected intensity ratios confirms that the physics of water photodissociation is operating exactly as laboratory experiments and theoretical models predict. This isn't surprising. Chemistry doesn't change across interstellar space, but it's profoundly reassuring. It means we can trust our interpretations that the tools we've developed to study solar system comets apply equally to visitors from other stellar systems. It also means we can quantify the outgassing. By modeling the observed absorption depth, astronomers estimate that 3I Atlas was producing water vapor at a rate of several hundred kilojoules during the October 24th observation. That's a substantial outflow, enough to create a coma several 100,000 kilometers in diameter, enough to explain the non-gravitational acceleration, enough to align with the 13% mass loss estimates. But hydroxyl emissions alone don't tell the full story. To understand 3I Atlas's composition comprehensively, we need to integrate data from across the electromagnetic spectrum. Enter JWST. In August 2025, the James Webb Space Telescope turned its infrared instruments toward 3I Atlas and detected carbon dioxide CO2 and hydrogen cyanide HCN in the comet's outgassing products. These molecules sublimate at different temperatures and from different ice matrices than water. Carbon dioxide ice vaporizes at greater solar distances than water ice, meaning CO2 outgassing begins farther from the sun. Hydrogen cyanide, meanwhile, is a trace component in cometary ices formed through chemical reactions in the cold molecular clouds where comets originate. Its presence indicates that 3I Atlas's progenitor environment included nitrogen and carbon chemistry, typical of dense interstellar gas clouds. Hubble Space Telescope contributed its own observations in September 2025 using ultraviolet spectroscopy to detect water vapor directly, H2O molecules, before they dissociate into OH, H, and H. This confirmed that the hydroxyl radicals MeerKAT detected originated from water sublimation, not from some exotic chemistry unique to interstellar comets. The convergence of these observations, radio detecting OH, infrared detecting CO2 and HCN, ultraviolet detecting H2O, creates a chemical profile of 3I Atlas that's both familiar and alien. Familiar because the major constituents mirror those found in solar system comets: water ice, carbon dioxide ice, trace organics. Alien because the ratios and abundances hint at formation conditions different from the sun's protoplanetary disk. Then there's the nickel vapor. In October 2025, optical spectroscopy detected neutral nickel atoms in 3I Atlas's coma, an unusual finding. Nickel isn't a volatile compound. It's a metal that requires extremely high temperatures to vaporize. Its presence suggests either that 3I Atlas contains metallic grains that sublimate under solar heating, or that subsurface pockets of material are reaching temperatures high enough to release refractory metals. This is atypical. Solar system comets occasionally show sodium or iron emissions, but nickel is rare. Its detection in 3I Atlas hints at compositional differences rooted in its interstellar origin. Perhaps the stellar nebula where it formed had different metal abundances than our own, seeding cometary material with elements that wouldn't normally appear in solar system objects. This chemical inventory, water, carbon dioxide, hydrogen cyanide, hydroxyl radicals, nickel vapor, paints a picture of a comet that formed in an extremely cold, chemically rich environment around another star. The high volatile contents suggest formation beyond the frost line of its parent star, in a region where temperatures were low enough for water and carbon dioxide to condense into solid ice. The presence of HCN indicates complex organic chemistry, the kind that occurs in dense molecular clouds, where ultraviolet radiation from nearby stars hasn't penetrated deeply enough to destroy fragile molecules. The nickel suggests either a metal-rich protoplanetary disk or unique thermal processing that concentrated refractory elements. But here's the profound implication. By studying the chemistry of 3I Atlas through radio, infrared, ultraviolet, and optical observations, we're not just learning about one object, we're sampling another stellar system. Every molecule detected, every absorption line measured, every spectroscopic signature decoded is a data point about the disk of gas and dust that surrounded an alien star billions of years ago. 3I Atlas is a frozen archive, a messenger carrying information about conditions we can never observe directly, and the hydroxyl lines at 1665 and 1667 MHz. They're one sentence in a much longer text, a chemical paragraph, that tells us water existed in that distant system, that it condensed into ice, that it survived the journey through interstellar space, and that now, illuminated by our sun, it's sublimating back into vapor, completing a cycle that began light years away. Timing in astronomy isn't just about convenience, it's about physics. The October 24, 2025 observation of 3I Atlas by Meerkat wasn't a random choice on a researcher's calendar. It was a carefully calculated necessity dictated by celestial mechanics and the relentless constraints of solar proximity. To understand why this date mattered so profoundly, we need to appreciate the geometry of what astronomers call solar conjunction. The period when a celestial object passes behind the sun from Earth's perspective, rendering it temporarily unobservable from our planet. 3I Atlas was racing toward perihelion, its closest approach to the sun, scheduled for October 30th, 2025. 6 days. That's how much time separated the Meerkat observation from the moment when outgassing would reach maximum intensity, when solar heating would penetrate deepest into the comet's nucleus, when water production rates would peak, and the hydroxyl envelope would achieve its greatest density. In an ideal universe, astronomers would observe during perihelion itself, capturing data at the exact moment of maximum activity. But the universe isn't ideal, and the sun doesn't cooperate with observation schedules. On October 24th, 3I Atlas was positioned just 3.76 degrees from the sun, as viewed from Earth. To put that in perspective, the sun's angular diameter is about 0.5 degrees. 3I Atlas was less than 8 solar widths away from the most powerful source of radio noise in the inner solar system. Observing anything at radio wavelengths that close to the sun is an exercise in filtering miracles. The sun is a seething ball of plasma, generating electromagnetic radiation across the entire spectrum, from gamma rays to radio waves. At 1600 megahertz Meerkat's target frequency, the Sun roars with emission from thermal Bremsstrahlung, synchrotron radiation from charged particles spiraling in magnetic fields, and transient bursts from solar flares. This noise floods radio receivers, overwhelming faint signals from distant or nearby objects. Engineers call it the solar radio background, and it's the bane of any astronomer trying to study objects in the Sun's vicinity. To detect 3I Atlas's hydroxyl signature through this cacophony required extraordinary sensitivity, advanced calibration algorithms, and a bit of luck that solar activity remained relatively quiet during the observation window. But why risk observing under such difficult conditions? Because after October 30th, 3I Atlas would vanish. Not literally, it would continue its trajectory through space, following the hyperbolic path that would eventually eject it from the solar system entirely. But from Earth's vantage point, it would pass behind the Sun, entering solar conjunction, a phase where its angular separation from the Sun became so small that observing it safely and effectively became impossible. Solar conjunction isn't brief. Depending on the object's trajectory and Earth's orbital motion, conjunction can last weeks or even months. For 3I Atlas, models predicted that it would remain unobservable from Earth through mid-November, possibly longer. By the time it emerged from behind the Sun, it would be moving away, cooling with outgassing rates declining as solar flux decreased. The October 24th observation window represented one of the last opportunities to capture ground-based data during peak activity. And it wasn't just ground-based telescopes watching. Multiple space agencies coordinated observations during this critical period, knowing that conjunction would sever most Earthbound opportunities. ESA's JUICE spacecraft en route to Jupiter captured distant optical images. NASA's Parker Solar Probe, designed to study the Sun from within its corona, adjusted its instruments to search for 3I Atlas during its close solar approach. Mars orbiters turned their cameras skyward, using their unique vantage point from the red planet to observe angles inaccessible from Earth. This was a coordinated multi-platform observational campaign, a scientific full-court press to extract every possible data point before 3I Atlas disappeared into the Sun's glare. Yet among all these instruments, only Meerkat captured the radio spectrum. Parker Solar Probe detected no anomalous signals despite its proximity. Mars orbiters provided optical context, but no spectroscopic breakthroughs. JUICE's images confirmed the comet's position, but added little chemically. The hydroxyl absorption lines at 1665 and 1667 MHz remained Meerkat's singular achievement, a testament to the array's sensitivity and the observational skill of the team operating it. This highlights a critical point often overlooked in popular science. Not all telescopes are created equal, and not all observations are interchangeable. Radio astronomy occupies a unique niche in the electromagnetic spectrum, revealing phenomena invisible to optical, infrared, and ultraviolet instruments. The fact that Meerkat succeeded where others couldn't wasn't a failure of those other instruments. It was a demonstration of complementary capability, of the necessity to observe celestial objects across the full spectrum to understand them fully. The October 24th observation also underscores the ephemeral nature of astronomical opportunities. 3I Atlas will never return. Its hyperbolic trajectory ensures it's a one-time visitor, an object that will spend the next million years or more traveling through the Milky Way's spiral arms, untethered to any star, until perhaps it encounters another stellar system or drifts into the galactic outskirts. The data Meerkat collected on October 24th, those absorption lines at 1665 and 1667 MHz, are irreplaceable. They represent a narrow temporal window when technology, celestial geometry, and human curiosity aligned. Miss that window and the opportunity vanishes, irrecoverable. This is what drives astronomers to push instruments to their limits, to observe under challenging conditions, to coordinate across institutions and continents. Because in astronomy, second chances are rare and regret is permanent. Let's strip away the technical veneer for a moment and ask a fundamental question. What does it mean for something to emit a natural signal at 1600 megahertz? Because when most people hear radio signal from space, their minds leap immediately to SETI, to alien civilizations, to carefully modulated messages encoded in electromagnetic waves. That's not what Meerkat detected. The signal from 3I Atlas is natural, unintentional, unmodulated, a consequence of physics rather than intelligence. But understanding why requires diving into the distinction between thermal and non-thermal emission, between signals that arise from heat and signals that do not arise from heat, that arise from more exotic processes. Thermal emission is what happens when matter has temperature. Anything above absolute zero emits electromagnetic radiation with the wavelength distribution determined by its temperature. Hot objects emit more at shorter wavelengths. This is why a heated metal glows red, then orange, then white as it gets hotter. At radio wavelengths, thermal emission from ordinary matter is extraordinarily faint, unless the object is either very hot or very large. A comet nucleus, typically a few kilometers across and heated to a few hundred Kelvin by sunlight, doesn't produce significant thermal radio emission. It's simply too small and too cold. So the 1600 megahertz emission from 3I Atlas isn't coming from the nucleus itself. Instead, it's coming from the coma, the cloud of gas and dust surrounding the nucleus. But even then, it's not thermal emission in the classical sense. The signal arises from hydroxyl radicals in the coma interacting with solar radiation. Here's the mechanism. Sunlight at optical wavelengths, visible. When a photon with the right energy hits a hydroxyl molecule, it can excite the molecule to a higher energy state. The molecule then re-emits that energy as it relaxes back to its ground state, but not necessarily at the same wavelength. Some of this re-emission occurs at radio frequencies, specifically around 1600 megahertz. This process is called maser emission in some contexts, like a laser but for microwaves. However, the hydroxyl emission from a comet S coma is typically much weaker than astronomical masers found in star-forming regions. So, astronomers classify it as natural radio emission rather than true maser emission. The absorption notches at 1065 and 1267 megahertz add another layer to the story. These aren't emissions, they're absorptions. Radio waves at these specific frequencies, generated either by background cosmic sources or by emission from other regions of the coma, pass through the hydroxyl cloud and get partially absorbed. The OH radicals preferentially absorb photons at 1665 and 1667 milliamps because these frequencies correspond to rotational transitions in the molecule's quantum energy structure. Every molecule has rotational states, ways it can spin in space, and transitions between these states require or release specific energies. For hydroxyl, those energies match photons with frequencies of 1665 and 1667 megahertz. When radio waves at these frequencies encounter OH molecules, the photons get absorbed, pumping the molecules to higher rotational states. The result is a dip in the spectrum at those frequencies, a dark line where brightness should exist. This is why the Meerkat detection is classified as a spectrum rather than a simple signal. A signal is just intensity over time, a fluctuation, a pulse, a pattern. A spectrum is intensity across multiple frequencies, revealing structure, revealing chemistry. The 1600 MHz continuum emission with notches at 1665 and 1667 MHz is a spectroscopic signature as unmistakable as a barcode. And, like a barcode, it can be decoded. The depth of the absorption lines tells us the column density of hydroxyl radicals along our line of sight, how many OH molecules the radio waves pass through. The width of the lines tells us about velocity dispersion, about how fast the molecules are moving relative to each other, which in turn tells us about the temperature of the gas. The intensity ratio between the 1665 MHz and 1667 MHz lines reveals whether the population distribution among rotational states is thermalized in equilibrium or whether non-thermal processes like solar pumping are affecting the populations. From the MeerKAT data, astronomers can extract water production rates. Here's how. The hydroxyl density in the coma is directly related to how much water is sublimating from the nucleus. Every water molecule that sublimates eventually becomes one hydroxyl radical after photodissociation. By modeling the hydroxyl distribution and accounting for the time it takes for dissociation to occur, researchers can backtrack to the water sublimation rate at the nucleus. For 3I Atlas on October 24th, the estimated rate was several hundred kg/s. Not the highest ever measured, but substantial enough to classify the comet as moderately active. For comparison, Hale-Bopp, one of the brightest comets in recent history, was producing water at tens of thousands of kilograms per second at its peak. So 3I Atlas isn't a giant, but it's not inactive either. Now let's address the elephant in the room, the persistent internet rumors about the 1420 MHz Fibonacci signal. This supposed detection, which allegedly showed a sequence of radio pulses following the Fibonacci sequence 1, 1, 2, 3, 5, 8, never happened. No astronomical institution, not MeerKAT, not Breakthrough Listen, not SETI Institute, not any credible observatory has ever released data supporting this claim. The rumor appears to have originated from speculative social media posts, conflating the legitimate MeerKAT detection at 1,600 MHz with completely fictional claims about alien communication at 1420 MHz. The 1420 MHz frequency is famous in SETI circles because it's the emission frequency of neutral hydrogen, the most abundant element in the universe. It's often called the water hole because hydroxyl, OH, emits nearby, and together hydrogen and hydroxyl combine to form water. H plus OH equals H2O, leading to whimsical speculation that aliens might use this frequency range to broadcast. But whimsy isn't data. There is no Fibonacci signal. There never was. The MeerKAT detection is legitimate astrophysics, hydroxyl absorption lines arising from photochemistry, not extraterrestrial engineering. What makes this distinction so important is scientific integrity. When we conflate real discoveries with hoaxes, we undermine public understanding of how science operates. The MeerKAT observation is extraordinary without needing embellishment. It's the first radio spectrum from an interstellar object. It confirms that we can study the chemistry of visitors from other stellar systems using Earth-based instruments. It opens a new observational avenue for future interstellar comets. These achievements stand on rigorous analysis, peer-reviewed methods, and reproducible data. That's the story worth telling, and it's compelling precisely because it's true. Inventing alien signals trivializes the genuine achievement and distracts from the real scientific questions. What does the hydroxyl distribution tell us about the nucleus's rotation and outgassing asymmetry? How do interstellar comets compare chemically to solar system comets? Can we use radio observations to predict a comet's future activity? These are the questions driving research, and they're grounded in the spectrum MeerKAT captured, a spectrum that exists, that was measured, that represents the voice of an object born under alien skies. If you've been following closely, you've noticed the fracture line running through this story. the place where the data stops making intuitive sense. On one hand, we have overwhelming evidence of outgassing. Meerkat's hydroxyl detection proves water is sublimating and photodissociating. Hubble's ultraviolet spectroscopy confirms water vapor presence. JWST's infrared instruments detected carbon dioxide and hydrogen cyanide, both volatile gases escaping the nucleus. Non-gravitational acceleration measurements show that gas jets are pushing 3I Atlas off its gravitationally predicted path. And the mass loss estimate, 13% of the comet's total mass shed between initial detection and perihelion, indicates catastrophic levels of activity. Every quantitative measurement screams active comet. On the other hand, we have images, photographs from multiple observatories showing 3I Atlas as a compact, structurally ambiguous blob of light with no visible tail. Not a faint tail, not a diffuse tail, no tail. And that's the paradox, because tails are where the outgassed material goes. When volatiles sublimate from a comet's nucleus, they don't just vanish. They stream into space, forming the coma immediately around the nucleus and the tail that stretches millions of kilometers behind. Dust particles entrained in the gas reflect sunlight, creating the visually spectacular structures we photograph and marvel at. Ion tails glow as solar wind energizes the gas molecules. These aren't optional features of cometary activity. They're inevitable consequences of physics. So, where are they? Hypothesis 1 remains the most scientifically conservative: dust depletion. Radio telescopes detect gas. Optical telescopes primarily see dust. If 3I Atlas's composition is extremely gas-rich but dust-poor, then instruments sensitive to volatiles would detect vigorous activity, while optical observations revealed little. This scenario requires a formation environment or evolutionary history that minimized dust content. Perhaps the comet formed in a region of its protoplanetary disk where larger grains had already been swept up by planetary formation, leaving only fine-grained ice and volatile compounds. Or perhaps it experienced thermal processing during its journey through interstellar space, with cosmic rays and ambient radiation gradually eroding dust particles while preserving subsurface ice. Under this hypothesis, the hydroxyl emissions and non-gravitational acceleration are driven by pure gas outgassing with insufficient dust to create optically visible tails. Hypothesis 2 introduces geometry, asymmetric jetting with unfavorable viewing angles. Comets aren't spherically symmetric. Their surfaces are patchy, with active regions where sunlight directly heats volatile-rich patches and dormant regions covered by insulating dust mantles. If 3I Atlas has major outgassing vents on the hemisphere facing away from Earth during our observation windows, then the jets and the dust they carry would stream in directions we can't see. The hydroxyl coma, being more diffuse and expanding over time, would eventually become visible because it spread spherically. But the concentrated jets responsible for tail formation would remain hidden. This scenario is testable as 3I Atlas's rotation carries different hemispheres into sunlight. We'd expect time-variable activity. And if future observations from spacecraft in different orbital positions detect jets invisible from Earth, this hypothesis gains credibility. Hypothesis 3 delves into compositional exotica, interstellar comets formed around other stars in protoplanetary disks with potentially different chemical inventories than our Sun's nebula. Maybe 3I Atlas is dominated by supervolatiles, compounds like carbon monoxide or nitrogen that sublimate at much greater solar distances than water. These substances could have driven intense outgassing when the comet was still beyond Earth's orbit, depleting the nucleus of its most volatile ices before optical observers started tracking it. By the time 3I Atlas reached perihelion, only less volatile components like water remained, producing the hydroxyl signatures Meerkat detected, but at lower total rates than the earlier supervolatile outburst. This stage depletion would reconcile the evidence of past high activity, 13% mass loss, with the currently sedate visual appearance. Hypothesis 4 is the cruelest: observational limitations masking real structures. Imaging 3I Atlas at 3.76 degrees from the Sun means fighting immense scattered sunlight. Earth's atmosphere scatters blue light efficiently, creating the daytime sky brightness. Interplanetary dust scatters sunlight throughout the inner solar system, producing zodiacal light. Observing a faint comet against this blazing background is like trying to photograph a candle flame at noon while staring near the sun. Tail structures, especially diffuse gas tails or tails composed of extremely fine dust, could be present but drowned in glare, falling below detection thresholds. Longer exposures would risk saturating the nucleus's light and wouldn't necessarily reveal fainter extensions. Different filters optimize for specific emission lines, sodium, carbon monoxide, CN, might reveal structures invisible in broadband imaging. But these specialized observations require telescope time, clear skies, and precise timing, all of which are precious commodities in observational astronomy. What tips the scales toward any particular hypothesis? Right now, nothing definitively. Each explains some observations while leaving others ambiguous. And that's not a failure of science. It's science operating exactly as designed, proposing testable explanations and seeking data to discriminate among them. The non-gravitational acceleration is particularly telling. You can't fake rocket thrust. If gas jets weren't escaping asymmetrically, 3I Atlas would follow a purely Keplerian orbit dictated by gravity alone. The measured deviations require sustained directional momentum transfer, which means jets are real even if we can't see them optically. This strongly supports the asymmetric jetting hypothesis or the dust-poor composition hypothesis, because both allow gas jets to exist without producing visible dust tails. The mass loss estimate independently supports high activity. 13% is enormous. Objects don't shed that much mass passively. It requires aggressive sublimation, fracturing, possibly fragmentation events. Yet 3I Atlas remains coherent in imaging, no secondary nuclei, no spreading debris field. This suggests either that the mass was lost as pure gas, dust-poor hypothesis, or that fragmentations occurred, but the pieces remained gravitationally bound or haven't separated enough for optical resolution, which seems unlikely given the magnitude of mass loss. Alternatively, the 13% figure might be uncertain, derived from brightness models that assume certain albedo and size parameters. If those assumptions are wrong, the actual mass loss could be lower, reducing the severity of the paradox. Ultimately, the paradox exists because we're trying to reconcile two different types of observation: direct chemical detection via spectroscopy versus indirect structural inference from imaging. Chemistry is quantitative. It measures concentrations, production rates, molecular abundances with precision. Imaging is interpretive. It shows morphology, structure, context, but requires assumptions about what you're seeing. When chemistry says active and imaging says inactive, the truth likely lies in nuance. The comet is active, but in ways that don't produce the optical signatures we expect. And that nuance is where discovery happens, where our models get refined, where we learn that interstellar comets don't have to behave like solar system comets just because they share the label Comet. October 24, 2025 wasn't just about 3I Atlas. It was a proof of concept, a demonstration that radio astronomy can contribute meaningfully to the study of interstellar objects, a field that until Meerkat's detection had been dominated by optical and infrared observations. This matters because radio wavelengths offer capabilities that other parts of the spectrum can't match, and understanding those capabilities reshapes how we'll approach future visitors. First, let's talk about solar proximity. Optical telescopes struggle when objects pass close to the sun. Scattered sunlight, thermal heating of instruments, and the sheer danger of pointing delicate mirrors near the solar disk all conspire to create observational blackout zones. Radio telescopes face different constraints. Yes, the sun emits radio waves, lots of them, but radio instruments can observe much closer to the sun than optical telescopes because radio waves do not carry the same intensity of thermal energy. And because radio arrays can use interferometric techniques to null out the sun's contribution to the signal, Meerkat observed 3I Atlas at 3.76 degrand from the sun, an angular separation where optical observations were severely compromised. This proximity advantage means that radio telescopes can study comets during their most active phases, perihelion and immediately before and after, when solar heating drives maximum outgassing. Second, radio observations provide quantitative chemistry. Optical imaging tells us where dust is and how it's distributed. Infrared spectroscopy identifies molecular species through vibrational transitions. But radio spectroscopy, particularly hydroxyl absorption lines, directly measures gas production rates. From the depth and shape of those absorption features, astronomers extract water sublimation rates, coma temperatures, expansion velocities, and total volatile inventories. These are hard numbers. KGS, Kelvin temperatures, kmss velocities that feed directly into cometary outgassing models. You can't get that level of detail from a photograph. Third, radio telescopes are less affected by weather and observing conditions. Optical astronomy depends on clear skies, stable atmospheres, and minimal light pollution. A passing cloud can ruin an observation. Radio waves penetrate clouds, rain, and atmospheric turbulence with minimal attenuation. Meerkat could observe 3I Atlas during conditions that would ground optical telescopes. This reliability means radio observations can fill gaps in coverage, providing continuity when optical and infrared instruments are offline. The technological side matters too. Meerkat's success required sensitivity at the cutting edge of current radio telescope design. Older arrays, like the Very Large Array in New Mexico or Arecibo before its collapse, might have struggled with a signal this faint from an object this small. But Meerkat, commissioned in 2018 with modern receivers and digital processing, had the capability to pull this detection out of the noise. This isn't just a win for one instrument, it's a roadmap for future facilities. The Square Kilometre Array, SKA, currently under construction in South Africa and Australia, will be orders of magnitude more sensitive than Meerkat. When the next interstellar visitor arrives, and given that we've detected 3 in the past 8 years, the next one is statistically due within a decade, SKA could detect hydroxyl emissions from farther away track comets for longer durations and resolve spatial structure within their Comet. We're on the cusp of turning radio observations of interstellar objects from a novelty into a standard tool. And it's not just about comets. Interstellar objects encompass a range of types. 1I Oumuamua was almost certainly not a comet. No detectable outgassing, no coma, a trajectory consistent with an inert body. If future interstellar visitors include asteroids or more Oumuamua-like objects, radio observations could still contribute by ruling out cometary activity definitively, constraining surface composition through radar reflectivity, or detecting secondary phenomena like outgassing triggered by internal heat sources. The methodology Meerkat demonstrated, targeted radio spectroscopy during optimal solar proximity, transfers directly to any future object. There's a broader implication here about diversification of observational methods. For too long, Interstellar object studies have relied on a narrow slice of the electromagnetic spectrum. Optical telescopes find them, track them, image them. Infrared instruments add spectroscopy. Ultraviolet telescopes occasionally contribute, but radio astronomy was sidelined, assumed to be irrelevant because the first two interstellar objects yielded nothing at radio wavelengths. Meerkat proved that assumption wrong, and in doing so, it reminded the astronomical community that absence of evidence isn't evidence of absence. Just because 2I Borisov didn't produce detectable radio emissions doesn't mean no interstellar comet ever will. Every object is different, every composition unique, every trajectory subject to variables we can't predict. The only way to know what a radio telescope will see is to point it and observe. October 24th validated that philosophy. Looking forward, the template is clear. When the next interstellar visitor is detected, the response should be immediate and multi-wavelength. Optical observatories will track its trajectory and monitor its morphology. Infrared telescopes will characterize its thermal emission and chemical composition. Ultraviolet instruments will search for volatile species, and radio arrays will listen for hydroxyl lines, water mazes, or any other signatures of outgassing or surface activity. This coordinated approach maximizes the science return, ensuring that no data goes uncollected because an instrument class was assumed to be inapplicable. The discovery on October 24th wasn't just about hearing 3I Atlas. It was about learning to listen in the first place. The story of 3I Atlas didn't end when it passed behind the sun. In many ways, that was just the intermission. Solar conjunction, the weeks when Earth's line of sight to the comet passed too close to the sun for safe observation, was always going to be temporary. Orbital mechanics dictate that as Earth continues its path around the sun and 3I Atlas moves along its hyperbolic trajectory, the angular separation will increase, bringing the comet back into observable space. That emergence is scheduled for early December 2025, and the astronomical community is ready. Hubble Space Telescope has observation time allocated for ultraviolet spectroscopy in mid-December. The science goal is specific: determine sulfur to oxygen ratios in 3I Atlas's coma. Sulfur abundance is a diagnostic of formation conditions, particularly temperature. Comets formed in colder regions of protoplanetary disks retain more volatile sulfur compounds, like hydrogen sulfide, H2S, while those formed closer to their parent stars lose sulfur preferentially. By comparing sulfur to oxygen, a more refractory, stable element, Hubble's measurements will constrain the temperature range where 3I Atlas's ice is condensed. This is indirect stellar archaeology, using a comet's chemistry to infer properties of a star system we'll likely never observe directly. JWST is also returning to 3I Atlas in December. The previous observations in August detected carbon dioxide and hydrogen cyanide pre-perihelion. December observations will capture post-perihelion chemistry, revealing whether the heat of perihelion passage altered the comet's outgassing profile. Did the intense solar flux near 203 million kilometers trigger the sublimation of deeper, more refractory ices? Are there new molecular species appearing in the coma that weren't present in August? Comparing before and after chemistry is rare in cometary science. Most comets don't get studied with JWST's capabilities at multiple epochs. 3I Atlas's interstellar origin makes this comparison even more valuable, providing a case study in how objects formed around other stars respond to our sun's radiation. Radio telescopes, including Meerkat, will continue monitoring for hydroxyl emission. The expectation is that as 3I Atlas moves farther from the sun, outgassing will decline, and with it, the density of hydroxyl radicals in the coma. Tracking this decline will test models of how water production scales with solar distance. For solar system comets, we have decades of data showing that water sublimation follows predictable curves based on heliocentric distance. Does 3I Atlas follow the same curves, or does its interstellar origin introduce deviations? If its ice is purer, less contaminated by dust, it might sublimate more efficiently at greater distances. Alternatively, if early supervolatile loss depleted its near-surface layers, water production might drop off faster than models predict. The observational geometry in December also changes. 3I Atlas will be moving through the constellations Virgo and Leo, gradually increasing its distance from both the Sun and Earth. Its brightness will fade. Estimates suggest it will dim to magnitude 12 or fainter by late December, below naked eye visibility, but still accessible to medium-sized telescopes. The fading is inevitable. Comets brighten as they approach the Sun and dim as they recede. But fainter doesn't mean less interesting. In fact, the dimming phase often reveals structural features obscured by peak brightness, as the overwhelming light from the nucleus diminishes and more diffuse coma components become relatively more prominent. If 3I Atlas has a faint tail that was invisible against perihelion glare, December might be when it finally becomes visible. There's also the question of rotation and surface heterogeneity. All comets rotate, and their surfaces are patchy. Active regions where volatile-rich ice is exposed sublimate vigorously when illuminated, while dormant regions covered by dust mantles remain inert. As a comet rotates, different regions face the Sun, causing outgassing to vary periodically. Light curve observations, monitoring brightness over time, can reveal rotation periods and identify active regions. For 3I Atlas, systematic light curve monitoring in December could detect these variations, providing clues about its shape, spin state, and the distribution of active vents. If the tailless appearance in October was due to asymmetric jetting away from Earth's line of sight, rotation might eventually bring those jets into view. Long-term tracking extends beyond December. 3I Atlas will remain observable from Earth through early 2026, albeit increasingly faint and distant. Amateur astronomers with advanced equipment will contribute observations, adding data density that professional observatories, with their oversubscribed schedules, can't match. Citizen science has played a significant role in cometary research, discovering new comets, monitoring outbursts, and tracking long-term activity patterns. 3I Atlas, as only the third confirmed interstellar object, is a target of immense interest to the global amateur astronomy community. Their contributions, images, photometry, astrometry, will supplement professional datasets and extend the observational baseline. But there's a finite window. By mid-2026, 3I Atlas will be too faint for most Earth-based telescopes, and its angular position will make observations increasingly challenging. Unlike solar system comets that orbit the Sun and return, interstellar visitors are one-time encounters. Once 3I Atlas recedes beyond effective observation range, it's gone irretrievably. This imposes a sense of urgency on the research community. Every observation missed is an opportunity lost forever. This is why scheduling telescope time, coordinating multi-wavelength campaigns, and maximizing data quality are paramount. The December observation window isn't just a continuation of the October campaign. It's potentially the final chapter in humanity's study of 3I Atlas. And there's the existential reality. This could be the last well-studied interstellar comet for decades. Interstellar objects are rare. 1I Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas in 2025. 3 objects in 8 years sounds like a trend, suggesting one every 2 to 3 years. But small number statistics are treacherous. The discovery rate depends on survey sensitivity, sky coverage, and luck. Upcoming surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, scheduled to begin in 2025, will dramatically increase the detection rate of transient objects, including interstellar visitors. But until LSST is fully operational and has accumulated years of data, the next interstellar object could arrive tomorrow or a decade from now. We don't know. And that uncertainty makes every observation of 3I Atlas precious, a data point in a sparse data set that might not grow for years. Step back from the technical details, from the hydroxyl absorption lines and the orbital mechanics, and consider what 3I Atlas represents at the most fundamental level. It's a messenger, not in the intentional sense. It carries no encoded information, no deliberate communication from an alien civilization, but it is a physical sample of another star system, a tangible piece of a cosmic environment we can never visit, compressed into a few kilometers of ice and rock and hurled across the galaxy by gravitational interactions we can only infer. Every molecule in 3I Atlas condensed from a cloud of gas orbiting a star that isn't the Sun in a protoplanetary disk that formed billions of years ago, possibly before Earth even existed. That star might still be shining somewhere in the Milky Way, or it might have long since exhausted its fuel and faded. We don't know. 3I Atlas doesn't carry a return address, but it does carry data. The water ice that Meerkat detected sublimating into hydroxyl radicals formed in temperatures and pressures characteristic of the outer regions of a protoplanetary disk beyond the frost line, where water can condense. The carbon dioxide and hydrogen cyanide JWST detected imply a chemically rich environment, one where carbon and nitrogen were abundant and reactive. The nickel vapor hints at refractory processing or a metal-rich parent nebula. Every chemical signature is a constraint on the formation environment, a clue that narrows the possibilities. Over time, as we study more interstellar comets and accumulate chemical profiles, we'll build a statistical picture of protoplanetary disk conditions across the galaxy. We'll learn whether our solar system's chemical inventory is typical or unusual. We'll identify trends in volatile abundances that correlate with stellar mass or metallicity. This is comparative planetology extended to exoplanetary systems we can never directly image. The Meerkat detection adds a new dimension to this comparative project. Before October 24th, radio astronomy was absent from interstellar object characterization. Now it's part of the toolkit, and that's not a minor addition. Radio observations offer unique diagnostics unavailable at other wavelengths. Water production rates derived from hydroxyl lines are quantitative and time-resolved, allowing us to track how outgassing evolves as a comet moves through its orbit. Gas-to-dust ratios, inferred from radio versus optical brightness, constrain cometary structure and composition. The ability to observe close to the Sun extends our coverage into the period of maximum activity. These capabilities weren't hypothetical. They were proven on October 24th, when Meerkat captured a spectrum that shouldn't have existed according to precedent, but did, because nature doesn't read our textbooks. There's also a philosophical dimension to this work. Every interstellar object detected and studied chips away at the parochialism inherent in astronomy. For centuries, we've studied our solar system in exquisite detail, while observing other star systems only as distant points of light. Exoplanet research has begun bridging that gap, revealing that planets are common and diverse. But exoplanet characterization is indirect. Transit photometry, radial velocity measurements, thermal emission spectroscopy. We infer properties. We don't sample material. Interstellar objects are different. They're actual physical samples from other systems delivered to us by the galaxy's gravitational chaos. Studying them is the closest we can come to interstellar exploration without building starships. and this work is just beginning. When LSST begins operations, its wide-field surveys will detect interstellar objects at unprecedented rates. Estimates suggest dozens per year once the surveys mature. Not all will be comets, some will be asteroids, some might be objects unlike anything we've categorized. Each will require follow-up observations, rapid response coordination, multi-wavelength campaigns. The lessons learned from 3i Atlas, how to observe close to the sun, which instruments provide the most diagnostic data, how to distinguish interstellar composition from solar system analogues, will directly inform how we approach those future visitors. The infrastructure is being built now. Alert systems to notify observatories of new detections, pre-approved observing programs that can activate on short notice, international collaborations to share data and resources. 3i Atlas is the prototype mission, the proof that studying interstellar objects across the full electromagnetic spectrum is feasible and scientifically valuable. But let's not lose sight of the wonder. On October 24, 2025, a radio telescope in South Africa detected hydroxyl radicals around a comet that formed light years away under an alien sun in a disk of gas and dust we'll never see. Those hydroxyl molecules exist because water ice sublimated, because solar photons tore molecular bonds apart, because quantum mechanics dictates that OH radicals absorb radio waves at 1665 and 1667 millihertz. None of this required human intention or design. It happened because physics is universal, because chemistry operates the same way everywhere in the cosmos, because a comet's journey through the galaxy eventually intersected our tiny corner of space at a moment when we had the technology to listen. The impossible detection at 1600 MHz isn't just about 3i Atlas. It's about every future messenger we'll encounter, every spectrum we'll decode, every chemical secret we'll extract from ice that predates our solar system. It's about the conversations we're finally learning to have with objects born under alien suns. Not through transmitted signals, but through the silent language of spectroscopy, one absorption line at a time.